All right, cocktail fans, welcome back for another deep dive with yours truly.
And me.
You know how sometimes you spill your drink and it beads up on like your new jacket?
Right.
Or like when you see a fighter jet and you think, how is that thing not frozen solid up at 30,000 feet?
Yeah.
Well, today we're going to deep dive into hydrophobic materials.
Yeah, the stuff that basically laughs in the face of water.
And I'm very happy to be joined again by our expert on the subject,
Happy to be back.
who, as is typical, might get a little carried away with the science, but that's exactly what we're here for.
Well, it's not just water resistance. It's like how water interacts with surfaces at a microscopic level.
Okay, all right. I'm intrigued already.
Yeah.
So what exactly makes a material hydrophobic?
Sure.
I mean, we see the water beating up and rolling off,
Mhm.
but what's actually happening like beneath the surface?
So at a molecular level, it's all about the interplay of forces.
Okay.
So you see water molecules, they love to stick together.
Right.
That's what we call surface tension. And they form this like cohesive film, almost like a tiny little water balloon.
I see.
And hydrophobic materials, on the other hand, they have what we call low surface energy,
Mm-hmm.
which basically means the water molecules would rather stick to each other than to the material.
So it's like the water's having a party,
Yeah,
and the hydrophobic materials, that one guest everyone's kind of avoiding.
you got it.
Yeah. Okay.
And because of this, the water tries to minimize its contact with the surface and forms those like characteristic beads.
Oh, very cool.
Yeah.
One of the things that really caught my eye is this concept of superhydrophobicity.
Yeah.
Is that just like a fancy way of saying like extra water repellent, or is there more to it than that?
It's a little more than just a fancy name.
Okay.
Superhydrophobic materials, they take water repellency to a whole new level.
Well-
Like think about a droplet of water on a surface.
Mm-hmm.
You know, the angle between that droplet and the surface, that's the contact angle.
Right.
So the larger that angle is, the more hydrophobic the surface.
Oh.
So superhydrophobic surfaces, they actually have contact angles greater than 150 degrees.
So the water is like bouncing off the surface.
Pretty much. Yeah, it's pretty amazing.
So where do we actually see this superhydrophobicity in action?
Well, I think one of the coolest examples actually comes from nature.
Okay.
Have you ever seen like a lotus leaf?
Oh, yeah? Sure.
And how the water just beads up and rolls right off?
Yeah, and it takes all the dirt and stuff with it.
Exactly. It carries away the dirt and debris with it.
So this is that lotus effect.
Yeah, exactly. The lotus effect.
That inspired like self-cleaning surfaces.
Right.
It's like those sci-fi movies where the spaceships just clean themselves.
Yeah, exactly.
So how does this self-cleaning thing actually work?
Sure. So the lotus leaf, it's not just hydrophobic.
Okay.
It actually has this unique microscopic structure.
Okay.
So imagine like tiny bumps and ridges. You can't even see them with the naked eye.
So it's not just the chemical makeup of the leaf, but it's like the actual texture
Exactly.
that makes it so water repellent.
Yeah. Yeah. These tiny structures, they create air pockets.
Okay.
And it further reduces the contact area between the water and the leaf's surface.
Right.
And then when the water rolls off, it carries away the dirt and debris, just like a natural little car wash.
And we've actually managed to mimic this in man-made materials.
I have, yeah.
Wow, that's crazy.
Yeah, so we see self-cleaning applications inspired by this lotus effect everywhere now.
Like where?
Self-cleaning windows, paints that resist dirt, even fabrics that stand free. It's all thanks to this manipulation of the surface and chemistry.
Now, speaking of fabrics, I know one of the factoids we were looking at mentioned nano coatings being used in rainproof fabrics.
Right?
So is my like old raincoat using nanotechnology?
It very well could be.
Wow.
Yeah, nano coatings are these incredibly thin layers of material applied to a surface,
Okay.
and they're often just a few atoms thick.
Wow.
Yeah, and they act like this invisible shield against the water without affecting like the look or feel of the fabric.
That's incredible. And I read that the military is even using nano coatings to protect electronics from getting damaged.
Right, yeah. Nano coatings are super vital in military applications.
Oh, you bet.
Yeah, for ensuring that like sensitive equipment like communications devices, sensors, all function flawlessly, even in really extreme environments.
So even in like a downpour,
Mm-hmm.
those electronics are staying dry.
That's the goal. Yeah.
That's a game changer for soldiers in the field.
Yeah, absolutely. And what's really fascinating is nanotechnology, it's not just confined to high-tech applications like the military.
Mhm.
It's closer to home than you think.
Oh, really? Like how?
Probably have a nano coating protecting the screen of your smartphone.
What? Really?
Yeah.
I had no idea.
Yeah.
That's so cool.
Yeah.
It's amazing how something so tiny can have like such a big impact.
I know, it's pretty amazing.
But let's shift gears a little bit. We've been talking a lot about keeping things dry.
Right.
What about the opposite problem? Ice.
Ah, yes. Ice. That's a challenge, especially for aviation. You see, ice formation on airplane wings can be like a major safety hazard,
Oh, yeah, of course.
and hydrophobic materials can actually play a key role in preventing that.
That's right, because another factoid mentioned ice-resistant materials being applied to airplane wings.
Right.
So how exactly do we stop ice from forming on something like an airplane wing?
Well, there's a couple approaches,
Great.
but one involves like manipulating the surface to prevent water droplets from freezing in the first place.
Okay.
So you remember how hydrophobic surfaces make it difficult for water to spread and make contact?
Right, the water beads up instead of like forming a thin layer.
Exactly. So this means that the water droplets are more likely to stay as like small isolated beads,
Uh-huh.
which have a lower chance of freezing.
Oh.
So it's like we're minimizing their opportunity to turn into ice.
It's like we're giving those water droplets less of a foothold to freeze onto the wing.
Exactly, yeah. Good way to put it.
Okay, very cool.
Yeah, but there's another approach too.
Oh, there is.
Yeah, and it's making it easier to remove any ice that does form.
Okay.
And hydrophobic surfaces can also help here too.
How so?
Well, they reduce the adhesion between the ice and the surface.
Oh.
So it makes it easier for the ice to break off either naturally or with a little help.
So the ice is like loosely attached instead of really clinging to the wing.
Right?
That must be a huge relief for pilots dealing with icy conditions.
Absolutely. These ice-resistant technologies, they're crucial for aviation safety.
Wow.
You know, making sure planes can take off and land safely even in challenging weather.
Wow. We've gone from water beating on lotus leaves to protecting military electronics and keeping airplanes safe from ice.
I know, it's pretty amazing.
These hydrophobic materials, they're everywhere.
They really are.
It's amazing how far-reaching they are. But I think it's time for us to take a little break,
Sounds good.
refresh our drinks, and when we come back, we're going to delve into the specific types of hydrophobic materials and how they're made, so stay tuned.
All right, see you soon. Welcome back to our deep dive.
So we talked about what hydrophobic materials can do.
Right.
You know, those amazing water-repelling properties. But now I'm curious about what kinds of materials are we talking about here?
Right.
What's like the secret sauce behind this hydrophobic magic?
Well, there's a whole spectrum of materials.
Yeah.
You know, everything from natural wonders to cutting-edge synthetic creations.
Right.
Some are probably more familiar than you think.
Okay.
Remember that trusty raincoat we talked about?
Uh-huh.
That's likely made with a fabric that's been coated in a hydrophobic material,
Like what?
like Teflon or silicone?
Teflon, isn't that the stuff on my nonstick pans?
Exactly.
So the same thing that keeps my eggs from sticking also keeps me dry in a downpour.
You got it. That's wild.
Teflon or polytetrafluoroethylene.
Wow, what a mouthful.
Right.
I'm going to stick with Teflon.
Yeah, much easier.
So Teflon, it's a synthetic polymer with incredibly low surface energy.
It is, and it's so slippery that practically nothing sticks to it.
Not even water.
Not even water. Okay, that makes sense. And silicone, isn't that used in things like sealants and waterproof sprays?
You're right, again.
Okay.
Silicone is another fantastic example of a hydrophobic material.
So versatile.
It is super versatile.
Wow.
You'll find it in everything from bathroom caulking to those waterproof sprays you use on your boots.
Okay, so we've got those polymers like Teflon and silicone. They're great for like everyday applications.
Right.
But what about those super hydrophobic surfactants we were talking about earlier?
Yeah.
Like, what are those made of?
That's where things get even more interesting.
Okay.
Super hydrophobic surfaces often combine a hydrophobic material
Right.
with a specific surface texture.
Okay, so like those microscopic bumps on the lotus leaf?
Exactly.
We can actually recreate those in a lab.
We can, yeah, using some pretty clever techniques.
So it's not just about the material itself, but the shape of its surface.
Right.
It's like those tiny bumps. They're creating a miniature obstacle course for water droplets.
That's a great way to visualize it. Imagine like a microscopic mountain range. The peaks of those mountains create air pockets, and that prevents water from fully contacting the surface.
Oh, that's cool.
Yeah, it amplifies the hydrophobic effect.
So how do we actually make those microscopic mountains?
Right.
Like, are we using tiny chisels and hammers?
Not quite.
Okay.
There's a number of techniques.
Okay.
One common method is etching,
Okay.
where we use chemicals to selectively remove material from a surface
Okay.
to create patterns and textures.
So it's like creating a miniature landscape on the material.
Exactly.
That's pretty high tech.
It is, yeah. Another technique is deposition,
Deposition.
where we deposit a thin layer of material onto a surface.
Okay.
We carefully control the deposition process to create those textures.
Okay.
You know, the ones that we need for super hydrophobicity.
So I'm sensing a theme here.
Yeah.
a lot of these superhydrophobic materials depend on nanotechnology.
You're right.
Are those nanocoatings we talked about earlier, are they used here as well?
You're spot on.
Oh.
Nanocoatings are a fantastic tool for creating superhydrophobic surfaces.
Cool.
They allow us to deposit that very thin layer of material, often just a few atoms thick.
Wow.
With precise control over the surface texture.
So these nanocoatings are like the ultimate artists?
They are.
Like carefully sculpting those microscopic mountains?
They are.
To create the perfect water-repelling surface?
Exactly. And they're not just limited to creating bumps and ridges either.
Oh, really?
Scientists are developing nanocoatings that can mimic intricate structures.
Wow.
That are found in nature.
Like what?
Like the scales on a butterfly's wing, or the hairs on a water strider's leg.
That's incredible.
Nature offers some pretty incredible inspiration.
That's so cool. So we're taking inspiration from nature's best engineers to create these incredible materials.
We are.
That's amazing. But I'm also curious about the other side of the coin.
Okay.
If there are materials that repel water, are there materials that actually attract water?
Of course. You know, kind of like the opposite of hydrophobic. We call those materials hydrophilic.
Hydrophilic.
They have high surface energy,
Okay.
which means water molecules are strongly attracted to them.
Okay, like what?
Think of materials like cotton or paper.
Right.
They just absorb water readily.
So it's like this constant tug of war between these two forces.
It is.
You know, hydrophobic materials are pushing water away.
Yeah.
Hydrophilic materials are pulling it in.
Yeah.
That makes me wonder, are there materials that are both hydrophobic and hydrophilic?
That's a great question, and the answer is yes.
Oh, there are?
Yeah.
Okay, what are those called?
We call those materials amphiphilic.
Amphiphilic.
They have regions that are hydrophobic
Okay.
and regions that are hydrophilic.
So like a material with a split personality.
Yeah, that's a great way to put it.
It can't decide if it wants to cuddle up to water or push it away.
Right.
That's wild.
But why would we want a material like that?
Yeah, like what's the benefit of having both properties?
Well, amphiphilic materials, they're incredibly useful, especially in biological systems.
Okay, how so?
Well, for example, think about cell membranes.
Okay.
They need to be both water-repelling and water-attracting.
To function properly.
Exactly.
Yeah.
So the hydrophobic part of the cell membrane keeps the cells inside separate
Right.
from the watery environment outside.
Right.
And then the hydrophilic part allows the cell to interact with its surroundings.
That's so cool. And we can actually harness these amphiphilic materials for all sorts of applications.
They can.
Yeah.
From creating more effective detergents to developing drug delivery systems
Oh, wow.
that can target specific cells in the body.
Wow. So we've gone from everyday materials like Teflon and silicone to high-tech super hydrophobic surfaces.
Yeah.
And now we're talking about these amphiphilic materials with their dual personalities.
I know, it's pretty cool.
It's clear why you find this field so exciting.
It is.
There's so much complexity at the molecular level.
Absolutely. It truly is a fascinating field, and there's so much more to explore.
There is.
And we haven't even touched on the potential of hydrophobic materials in areas like energy production,
Oh, wow.
water purification, even robotics.
This is what I love about these deep dives.
Yeah.
We always end up with more questions than answers,
That's right.
which is a good thing.
It is.
You know, it means we're sparking curiosity and encouraging people to keep learning.
Absolutely. The more we understand about these materials, the better equipped we are to utilize their potential.
Right.
And create innovative solutions to real-world challenges.
Well said. Well, folks, we've covered a lot of ground in this deep dive.
We have.
We've explored the science behind hydrophobicity,
Right.
the fascinating materials that exhibit these properties,
Yeah.
and the amazing applications they enable,
Right.
from keeping our clothes dry
Yeah.
to protecting sensitive electronics,
Mm-hmm.
and even potentially revolutionizing medicine and robotics.
Yeah, it's pretty amazing.
Hydrophobic materials are shaping our world
They are.
in some pretty profound ways.
Absolutely.
But our exploration doesn't end here.
No, it doesn't.
Join us in part 3, where we'll take a glimpse into the future of hydrophobic materials and the exciting possibilities that lie ahead.
Can't wait.
Okay, cocktail connoisseurs, we're back for the final pour in our deep dive into hydrophobic materials.
Cheers to that.
We've covered the science, we've talked about the materials and some really incredible applications, but I'm curious, what's next for these water-repelling, wonders? What does the future hold?
Oh, the future is brimming with possibilities.
Oh, really?
Yeah, we're really just beginning to tap into their full potential.
Okay.
I can't wait to see what innovations emerge in the coming years.
Well, don't keep us in suspense. Spill the beans. What kind of futuristic applications are we talking about?
Okay, well, imagine a world
Okay.
where our solar panels stay flawlessly clean and efficient even after like a dust storm or a downpour,
Okay.
thanks to superhydrophobic coatings. Or wind turbines that can just shrug off ice buildup, ensuring steady energy generation even in the harshest winters.
That would be incredible.
Right?
I mean, harnessing clean energy is already a huge step forward, but this would like supercharge these technologies. Exactly. Make them even more effective.
Right.
That's amazing.
And it's not just about energy.
Oh, it's not.
Hydrophobic materials hold incredible promise in the field of water purification as well.
Now, that's intriguing. How can a material that repels water help us clean water?
Well, think about oil spills,
Okay.
which are one of the most devastating environmental disasters.
Right.
One of the biggest challenges is separating the oil from the water.
Right.
Hydrophobic materials can help us create these highly selective filters
Okay.
or membranes that repel the oil but allow the water to pass through.
So it's like a microscopic bouncer at the club,
Exactly.
letting the good stuff in and keeping the troublemakers out.
You got it.
That's brilliant.
What about applications in the medical field?
We already touched upon drug delivery systems. Is there anything else on the horizon?
Absolutely.
Okay.
So picture this medical implants that resist bacterial attachment,
Okay.
which would drastically reduce the risk of infection,
Oh, wow.
or surgical tools that repel blood and other fluids,
Okay.
making procedures safer and more efficient.
That makes sense.
We could even see the development of artificial tissues that seamlessly integrate with the human body,
Wow.
all thanks to the magic of hydrophobic materials.
We're talking about revolutionizing healthcare.
We are.
And I bet those water-repelling properties would be incredibly useful in robotics as well.
Absolutely.
Yeah.
Imagine robots that can operate in wet or humid environments without breaking a sweat,
Right.
or robots with grippers that can handle really delicate objects
Okay.
without the risk of slippage.
That makes sense.
We might even see robots that can swim efficiently through water thanks to bio-inspired designs that mimic hydrophobic surfaces found in nature.
Wow. So we've gone from self-cleaning solar panels to clean water, life-saving medical devices, and robots that can swim.
I know, it's pretty amazing.
The possibilities seem endless.
They really are. And what excites me the most is we're still in the early stages of exploring the full potential of hydrophobic materials.
Wow.
As our understanding deepens and our fabrication techniques become more sophisticated,
Right.
we're bound to see even more innovative and unexpected applications emerge.
That's the beauty of science, always pushing the boundaries and revealing new wonders.
Absolutely.
So for our listeners who are now completely fascinated by hydrophobic materials,
Yeah.
what's the one key takeaway you want them to remember?
I would say hydrophobic materials are more than just a way to keep things dry.
Okay.
They represent a fundamental shift in how we think about material science.
Right.
They allow us to control how materials interact with their environment at the molecular level. And this has profound implications for so many different fields, from energy and medicine to environmental science and beyond.
It's not just about water beading. It's about opening up a whole new world of possibilities.
Right.
Well, folks, there you have it. We've reached the bottom of our deep dive into the fascinating world of hydrophobic materials. We hope you've enjoyed the journey as much as we have.
Cheers to that.
And a huge thank you to all of our listeners for joining us on this adventure. Remember to subscribe to The Deep Dive for more mind-extending explorations into the world of science and technology. Until next time, keep diving deep and stay curious.